spectroscopy of starlight was studied in great detail at the end of 19th century, at the beginning of 20th century. And a lot of women actually worked on that sort of analysis at the Harvard College Observatory. There were a lot of them. They were referred to as computers. They were not paid for the work that they've done, but some of them made fundamental breakthroughs in astronomy. During that work, they realized that different stars have different absorption spectra. So they started assigning alphabetical designation to different spectral classes. For instance, if you look at this spectral class O, there are very few absorption lines. Then, as you move down to a spectral class B, there are more absorption lines, and as you move down, there are more and more absorption lines. Initially, the letters were assigned according to a principle that everybody forgets now. But then people realized that basically what these spectral classes tell us is they tell us about the temperature of the star. Because if the star is very hot, like an O-type star, then all the electrons in the atom are already in the highest energy levels. And they cannot absorb light. They cannot move anywhere. Okay? Some photons could get absorbed, but very many are not absorbed. Then as you go to the spectral class B, there are more absorption lines because the star's atmosphere is at a lower temperature. So there are more absorption processes that can take place. And so on. As you move down to A, F, G, K, M, you have more and more absorption. So basically what these spectral classes tell us is they tell us about the temperature of the star. So as you go from O down to M, the temperature drops. And I ask you to know that, for instance, star B is hotter than star G, or that F is cooler than A, and that sort of stuff. And you will say, are you nuts? I mean, how can we remember this seemingly arbitrary assignment of letters? And there are several mnemonics that are often used by astronomy students to recall this. One that I like is, oh, be a fine girl and kiss me. The other one, in particular, if you live in the noisy dorm, could be, oh, big and furry gorilla, kill my roommate. So I'll give you a choice which one to use. So Sun is in spectral class G. Okay? So Sun belongs to this spectral class G. So in astronomy, the surface temperature and the spectral class are used as synonymous things. They mean one and the same things. You can hear astronomers talk about some star being of spectral class M. What he's really talking about, he's talking about the surface temperature of the star. So, and they are O, B, a fine girl and kiss me, right? And the temperature drops in this direction. So my suggestion is that on the exam, if there is a question where you have to determine there are some stars and their spectral class is specified, and you have to identify which one is the hottest and which one is the coldest, just write on the side of the exam script quickly this, and point the arrow in which tells you how the temperature varies, and then see what you have there, and then you can find out which one is hotter and which one is cooler. Okay? So then the surface temperature of the sun is a spectral class G. And that star in the knee of Orion that looked bluish when we talked about the connection between the color of the star and the surface temperature, it's actually a B-type star. And Betelgeuse, that enormous dying star whose diameter is about 800 times larger than the diameter of the sun, it is the spectral class M. It has a cool surface, hence it's red. So we now know how to find the distance to the star. We know how, once we know the distance, by measuring its brightness, how to determine its luminosity, right? We now know two ways how to determine the temperature, the surface temperature of the star, either through Wien's law or black body radiation law, or by finding out the spectral class of the star. There are certain number ranges associated with each spectral class, right? So it gives you the temperature range for the star. Once you have the temperature and the luminosity of the star, you can determine its radius by applying the Stefan-Boltzmann's law. And finally, you can determine the chemical composition of the star by looking at the absorption lines of its spectrum, by which spectral lines are missing because those photons got absorbed in the atmosphere of the star.